Right, so this video will be kicking off our Unit 3 lectures. Here we start to better blend together chemistry and biology, in particular in this unit focusing on organic chemistry. And I know a lot of you, being at the high school level, maybe never had a class that specifically dealt with organic chemistry, and often it is said to be pretty difficult, but I promise that once we begin breaking it down, it's really just a language about how these different molecular formulas are represented and how they build the molecules of life. So that's really what organic chemistry is. It's really life chemistry. Because a lot of these molecular formulas that we're going to be talking about are made in the human body and help sustain life in cells. So first, I wanted to show you this image of a protein. See, there's tons in here. Perfect almost thing of symmetry. Here, it's not necessarily all symmetrical. If you did look at all these small spiraled structures, they would be perfectly symmetrical. Sometimes your body can achieve that. But here in particular, each of these spirals are groups of amino acids or groups of their structure, and it looks pretty complex. This is the type of thing that your body can regularly produce. This protein actually works, this vault type container structure. And this protein almost acts as a cellular trash can, vault, and then carry it throughout the body to be processed by other waste mitigation means. Makes very similar vault protein types. And what we want to focus on, if we're looking at each of these, I wonder if I can zoom in here a bit, each of these squiggle type structures is comprised of molecules. And we're going to be talking about the composition and structure of those molecules. So going back to what is organic chemistry, it's really the chemistry of life. And even though there's over 100 elements on the periodic table, the atomic recipe for a human is actually pretty simplistic. So we have lots of carbon. As we know, carbon is an extremely, it's almost ubiquitous atom, right? It's in a ton of structures, and it's a very commonly used element. We're about 18% carbon. Then we've got hydrogen. We are about 10% hydrogen. Heavy on the oxygen. We are, I should be capitalizing these. You're about 65% oxygen. And about 3% nitrogen. So all of that, right, leads up to about 96%. So the remaining 4% or so is a sprinkling of about 20 other elements. And that's pretty spectacular when you think about it, right? There's over 100 elements, and really you come down to about 24 of them. So to understand the small scale of human lives and how cells work, focus on these 4 elements. That would be the C's, right? The H, the N, the O's. So those are the key role players in the composition of a human. Now, we had talked, I think very early on in this class, we said that in theory, you could have a group of atoms, and if you rearranged them in the right way, as long as you had the correct atoms and the correct amount of them, you could build something else. So let's say you were looking at a deer, say that is roughly the same weight as a human. They would have a similar atomic composition. So if you wanted to, you could take that frequently alluded to atomic size pair of tweezers, and you could pick apart the deer atom by atom, rearrange them, and you could comprise a human. So not that this would ever realistically occur, but the point I'm trying to make is that a lot of life is heavily comprised of these same atoms and roughly the same proportions of them. So what are the functional roles of these four atoms if they're so important? So we've got carbon. Carbon tends to act as the main structural atom. So let's say you're trying to build a house. Every house has some type of frame, or every large building has a scaffold, right? So because carbon is so prevalent, it is usually regarded as the frame. So from house to house, you might have, different furniture, different paint, different tile, but at the base of all of that, you're still looking at a frame or some type of bare structure holding up the house. And that's really what carbon plays a role at in organic chemistry. It's very versatile and can be put together in millions of ways. Actually, we want to move this bullet point because we'll talk about that later on. But say, for instance, here we've got about 13 carbon atoms. This here, as we see the way it stands, really acts as the bare organic structure. It's comprised of carbon. It can almost look like a spine of sorts. And that is serving as kind of the base model. You might add different accessories. Like we said, you might change up the paint, include a group here, a group here. But at the base, you're really looking at a carbon chain of sorts. Right, moving on to hydrogen. The role of hydrogen is, in a sense, to complete the frames of carbon. I don't want this bolded. So the hydrogen is sort of what we talked about. It's the floors, the walls. It's more than just the bare bones structure frame of a house. Every atom in a structure needs a correct number of bonds to be considered complete. And I might just back up here really quick. So, right, we jump from here, which is just our carbon chain structure, and now we jumped on here where we have this molecule that's saturated with hydrogen. So we not only have the 13 carbon, but we have these hydrogen atoms kind of filling in the gaps here. It's providing more to the molecule. And you'll remember from our annotated periodic table a while back, we know that carbon has 4 valence electrons, and so it's trying to either gain 4 or lose 4 in order to create a full shell. So if it needs 4 electrons, that probably means that it's forming 4 bonds, right? Carbon always needs 4 bonds. So we'll add here, carbon always wants 4 bonds. Nitrogen it wants 3 bonds, rarely 4 bonds. So we might as well get into the exceptions because we'll be talking about this at the end of the lecture. But nitrogen usually wants 3 bonds, right? Rarely it will have 4 bonds. And the last one, oxygen, wants 2 bonds, rarely 1 bond. So we can look at different examples here to exhibit this idea that carbon always needs 4 bonds. Now, all 4 of those bonds are not necessarily satisfied by 4 hydrogen atoms. And kind of the point that I'm trying to get across here is that really they just need a total of 4 bonds. It doesn't really matter which atom is on the other side of the bond. So if we look at this kind of this outside here, if you can see my mouse moving, we've got, if we look at the 4 bonds branching off this carbon, 1 is bonded to another carbon. So that's 1 of the 4 bonds. So the other 3 are hydrogen. Here, however, the next carbon over, it is bonded to 2 carbons. So 2 of the 4 necessary bonds are to other carbons. That only leaves 2 spaces left for hydrogen atoms. Now, even if we jump over more to the right side of the molecule, we've got carbon bonded to 3 other carbon atoms. So it only leaves 1 space left. It only needs 1 more bond to satisfy those valence shell asks. And so only 1 hydrogen atom is needed here. So in a sense, it's like when you're building a room, some rooms need different things to be considered complete. So your living room might need a couch, but does your kitchen necessarily need a couch? Not necessarily. So different atoms and different molecular structures need different amounts of bonds to be happy, and different things to fill those bonds. We're going to be continuing with the house analogy probably throughout most of organic chemistry, so you'll have to bear with me. All right, now we are moving on to oxygen and nitrogen. So these two are used to add in unique chemical behaviors and functions. To hydrocarbons. And actually, I should have backpedaled here. We need to specifically define what a hydrocarbon is, although it's probably pretty intuitive on the name. So hydrocarbons are molecules comprised of hydrogen and carbon atoms. Now, when it just has those 2 things, it's not necessarily a very reactive molecule. So adding different, let's say a little spice, some different atomic identities to the formula, that's where we start to get these unique chemical behaviors and functions arising. All right, so I'm going to continue with the spice comparison. Adding functional groups, or adding those groups with different atoms, is like adding pieces of spice writing the full statement here so later when you look at your notes you're not confused. And functional groups is the key vocabulary term here. And should have another bullet point here. in your body, in all the different types of molecules that carry out your cellular processes and comprise you, there are 30 functional groups that get added on to hydrocarbon molecules. And I know in this structure, so we'll just make a note here, or almost like illustrate. Oh, we want the outline. We want no fill. Right. So this here, we've got, two oxygen atoms and a hydrogen atom coming off of this carbon atom here. So that would be the functional group. So we kind of jump from our 13 carbons that are saturated with hydrogen in the above structure. And then we are adding a little bit of spice. We're adding a little bit of oxygen to the structure. And I know this is oxygen and nitrogen. I know in this structure here, we're not yet depicting nitrogen, but we'll have examples of those later in the lecture. I think, if we replace this oxygen atom with a nitrogen atom, you get the idea. All right, so it's a good thing that these structures were already added to your notes, right? Because it would end up being quite a pain to draw all these atoms and especially all the hydrogens, right? It's a huge pain to write down. There are actually different ways to represent organic formulas, so you don't necessarily have to draw this out in this way each time. So when we're talking about different kinds of organic formulas, we're basically saying different ways to draw organic compounds. And we need better ways to write this information down. It would be incredibly time consuming to draw out this complete structure every single time, right? And there's a couple different examples we're going to give here. So first is the molecular formula. So for example, just really quick format this correctly. Remember that the numbers are subscripts. So we've got this molecular formula here, 2 carbon atoms, 6 hydrogen atoms. This method of writing the molecular formula, it tells you the number of atoms. In a compound, but not how they are arranged. So here we know that there's 2 carbon atoms, we know that there's 6 hydrogen atoms, but we really don't know how those are oriented, right? We could take a guess, but we don't know for sure. And this third bullet point here is a little redundant, not how they're arranged. So the first is molecular formulas. That's a way to draw an organic compound. The second is kind of what we've been working with all along in our examples above. Those were the expanded structural formulas. So the example here, I've got, I think this would actually be propane. So that's 3 carbons and 8 hydrogen atoms. So unlike the molecular formula, the expanded structural formula shows you all the atoms in a compound and how they are arranged. But I'll put a disclaimer here, but it takes too long. There are better ways I'll actually make this a little smaller just so it's not cutting into my writing here. So that is the expanded structural formula. It shows all the hydrogen atoms, shows how everything's arranged. The next type presents, and this is where it starts to sound like an infomercial. It's like, you spend too much time writing out your expanded structural formulas. It's like that old commercial for the package shark. That lady's trying to open a package and she just kind of takes out a chainsaw and tries to open it. Then they present their product. The next thing that we're going to present in the lecture is the skeletal formula or the condensed formula. It's a different, almost a shortcut way of drawing these structures. But we're going to save that for the next video. So yeah, thank you for tuning into our intro to organic chemistry.